Hello, good afternoon and welcome. Have you ever wondered why we launch so many satellites into space? Or what type of information or knowledge is being produced by these satellites? Or maybe you're interested in learning how you can use Earth observation insights for your business or for your mission. Well, in this session, we will review delivering Earth observation data at scale with serverless and edge compute. It is my pleasure to introduce Joel Cumming, Alexander D'Souza, and Quentin Morse. Over to you, Joel.
Thanks for the introduction, Brian. Joel, if you would, tell us a little bit about Skywatch.
Yeah, I'm happy to. Thank you. Thanks, everybody, for coming. I know we're between you guys and happy hour, so thanks for that. Skywatch, a little bit about us. We were born out of a hackathon. Some of you may be familiar with the NASA Space Apps Challenge that happens concurrently in about 200 cities around the world. And Skywatch, our founders, they went to the 2014 event in Toronto. They didn't know each other, and they built a really cool project, ended up winning that hackathon, and got to go to the global event. They won the global event as well for best use of data. So pretty cool origin story. Fast forward to where we are now. We're a venture capital funded startup. We have some great investors here shown on the screen. Really, our value proposition is over 3 different areas. The first is we aggregate commercial Earth observation data to make it simple for anyone to use. So if you've tried to use commercial data today, maybe you've gone to a supplier and asked them for data. It's normally comes with a minimum spend and a contract that goes along with it. It can be pretty challenging. They have large customers. They're not necessarily interested in small ones. So we solve that problem. We also make the data available through a machine-to-machine API. So if you're building something at scale, you can do that through an API instead of just using a shopping cart checkout experience. The second value proposition is we have a product for satellite operators. So a lot of satellite operators, they need to spend a whole lot of money to build their satellite and get it into space, to worry about a lot of different things. One of the things they often don't think about or maybe don't prioritize is how they're going to sell that data once it's in space. So we have a product that allows them to do that. And lastly, our third value proposition is the data that actually comes off of both of those 2 systems. So as people are requesting imagery from us, then they can, we're seeing what's fulfilled, what's not fulfilled by different suppliers. So we can anonymize that information and show it to a satellite operator, let them make tactical and strategic decisions about how they place their orbit or what they capture. If there's a hot spot and nobody's collecting there, maybe they want to collect and they can deliver the data. So a little brief history about Skywatch.
Thanks, Joel. So Earth observation sounds pretty relevant, pretty interesting. But for those in the audience who don't understand what Earth observation is, could you give us a quick description of what that is?
Sure. So for the experts in the room, forgive me, but sort of starting from the basics, Earth observation is really the capturing of imagery using remote sensing, and generally that comes from a number of different platforms. So satellites are an obvious one. There's different types of satellites. There's multispectral satellites. Typically they come with a red, blue, and a green band, maybe some others on the spectrum. Hyperspectral is emerging as a larger technology, has a larger spectral wavelength typically, and you can slice that up into narrow bands and get some interesting information. There's also synthetic aperture radar, or SAR satellites, that use microwaves to penetrate weather and also send information back up to space. We can look at the reflectance of that. And then, of course, drones and balloons, or high-altitude platforms. Some of you may have remembered the balloon that flew over part of the US and Canada the last little while. There are also commercial companies, not just the Chinese, that are using it for nefarious or potentially nefarious purposes. So really, the goal with Earth observation data, if you think about it from an application development perspective, when you build apps, you want to instrument those apps so you can see what's happening with your users and with your systems. And with Earth observation data, we're really instrumenting the world, right? We're looking to be able to see all the changes that happen all over the world, and we can do that on a daily basis. So we often challenge our customers, what would you build if you could see everything on Earth every day?
So Joel, considering Skywatch is a venture-funded startup, can you tell us a little bit about what the market opportunity and size looks like?
Yeah, absolutely. So as you might imagine, venture capitalists look for big markets, and this one's pretty big. So according to Euroconsult, sort of a leading Earth observation and space consulting company, the market size in 2022 is about $4.6 billion. That's roughly going to double to almost $8 billion by 2031. And that significant amount of that growth is tied to a broad expansion in commercial Earth observation as well.
So, audience, what kind of companies do you all think take advantage of Earth observation data? if you would just use the QR code and type in the code as well and submit your answers, then we will proceed and take a look at those answers and take a look at what the greater Earth observation market looks like. Cool. If we could take a look at the results.
Got a smart audience.
Smart
here.
audience,
Yes.
yeah.
Wow, and it's late. Y'all are bright. Y'all are sharp. Thanks. We could go back. So, Joel, if you could tell us a little bit more about some of the case studies, but really if you could break down, where, what kind of industries and where we're seeing Earth observation data be used, that'd be helpful.
Absolutely. So the use cases I like the best are really the ones where we drive costs out of the value chain. But before we get to that, talk a little bit about regions and verticals here. So in this slide, you can see on the left are the different regions that consume Earth observation data. On the right are the different segments or verticals. So North America obviously dominates, followed by Europe and Asia in terms of location. And segments, defense is typically dominated. We are not focused on defense-related Earth observation delivery. There's lots of companies, satellite operators tend to do that directly. And there's some security reasons for that. We focus on the commercial market. So if you look below that defense bucket on the right, you'll see infrastructure, energy, natural resources being big chunks of that as well. So tons of market opportunity in a lot of different areas, and so we're excited about many of them.
So it appears that the market is pretty expansive. Could you go a level deeper and tell us a little bit more about the specific use case that you see?
Yeah, for sure. So as I mentioned, my favorite use cases are where we drive costs out. So in terms of oil and gas pipeline monitoring, we see opportunities. We have a customer who built software that is meant to target this market. And in the oil and gas world today, most companies are required to monitor their pipelines from overhead. And what that means is they have a fleet of helicopters and pilots. And those helicopters and pilots fly over these pipelines every week or every month. And if they see something that looks like it's going to encroach on that pipeline, they will lean over and take a picture of it. And then when they get back to the office, they'll decide, okay, are we going to send boots on the ground to go talk to this person who might be nearing this pipeline? But with Earth observation data, if you go to the next slide, you can automate a lot of this. So this particular customer of ours, they use open data from Sentinel-1, so SAR data, and they divide the whole oil and gas pipeline into 1 square kilometer cells. And along those cells then, they are looking, every revisit of that particular satellite, they're looking to see, is there change in that cell? And those green boxes are what actually returns from that synthetic aperture radar. And then on the right, you can see that change detection image. So yeah, we think something's changed, but now what is it? We need to find out. So this is where instead of the pilot leaning out and taking a picture, they can request high resolution Earth imagery from us. And if you go to the next slide, you can see this is their application. So that circle is where they've detected change, and they see the base image, the previous image is, there's nothing in this particular location, and then there's the change, and now we can visualize that with a high-resolution Earth observation image. The whole price of this product that basically does the same thing as the helicopters is about 75% less expensive than flying this fleet of helicopters. So love these types of use cases where you can eliminate costs when it's not a core competency. Nobody wants to fly helicopters, they just have to because of regulations.
So the oil and gas industry is a big one where we might see Earth observation data being used, but I know that we also have some agriculture customers. So how do you see Earth observation data being used in the agriculture industry?
Yeah, if I can take that one. Precision agriculture is a really interesting application for Earth observation imagery. As Joel alluded to earlier, we all know that light is divided into a spectrum, and when a satellite makes its acquisition, it's typically doing so in a number of different bands: red, green, blue, near infrared. And so it happens that chlorophyll is highly reflective in the near infrared. And really what that means is by examining the amount of light deposited in the near infrared, in the pixels or in a portion of the image, you can actually get a sense for the health of the vegetation that happens to be in that area. If you go to the next slide. So what you're seeing on the screen right now is actually a time series evolution of a photograph of the Earth. And so the gray areas tend to be barren soil. The brown is moist but still developing areas. And as the time series progresses, you notice it becomes increasingly green, which corresponds to highly developed vegetation. And so this is really interesting for a farmer who might want to know where do they invest limited resources such as fertilizer or machinery in order to improve the health of their crop. And instead of having to drive around and actually take those measurements themselves, with a single acquisition from space, one of our clients, CropSafe, incorporates this data into an application. And now a farmer on the ground in a single snapshot can assess the entire health of their crop from their phone.
So outside of oil and gas and precision agriculture, is there any other ways that spectral wavelengths can be used to derive insight?
Yeah, one of the most exciting for me is mining. So hyperspectral, Joel also mentioned, here we divide the light not just into red, green, blue, and near infrared, but into sometimes hundreds of really narrow spectral bands. And we can actually start to measure correlations in the image, both spectrally across the spectrum and spatially across the image domain. And so we've actually developed what's called a Bayesian convolutional unmixing network. It's a sophisticated type of neural network that we use to tease out those correlations. And then with a single image from space, we can actually determine the mineralogical topography of the entire scene with relatively high accuracy.
So these few use cases we've talked about seem maybe non-trivial or non-obvious, but one that strikes me as a possible use case for Earth observation data would be disasters, looking at disasters from above, so things like flooding and landslides and things of the sort. So how do you all see Earth observation data being used in these situations?
Yeah, we see it a lot. And so a great example is Hurricane Dorian that struck the Bahamas in 2019. Certainly there's lots of hurricanes that cause lots of damage, but in this case, there was rescuers and respondents going to provide aid, and they called on us actually to help them prioritize where they were going to focus. So if you go to the next slide, this is a time series of a place called Marsh Harbor in the Bahamas, a before and after. And so we were working with the Bohemian Air, Sea, and Rescue Association and the Third Wave Volunteers in this case, and they were asking us where they needed to prioritize and asking us for imagery. So because a lot of the infrastructure was wiped out, we were actually sending them satellite images through WhatsApp on the ground, but they were able to use that to help prioritize where they would go to provide the most value. So some other examples, forest fires are an obvious one. They've affected a lot of people in North America this summer. And in this example, this is from 2018 from the French River in Ontario. And you can see in this image, you can see part of the fire and how it grows, and then you see the burn scars that are existing after that. And so, understanding how to react when the fire is starting, where it may spread to, and then the damage that it's done afterwards is something that we see a lot of interest in as well.
Sure. So these seem like pretty important, relevant use cases for a lot. But also in journalism, there may be times when we need to monitor a conflict or something of that nature. So how do you see Earth observation data being used in the journalism industry?
Yeah, certainly there's a lot. I think one of my favorites is when, if you remember, in March of 2021, when the Evergreen got stuck in the Panama Canal. These types of images showed up on all sorts of different media outlets, and so it was really interesting because enthusiasts who wanted to get these images were side by side with journalists, but it was really interesting to try and understand, okay, what's happened? Is it still stuck? When are things going to move in the global supply chain again? And then also, construction monitoring, if you go to the next slide, is another use case that we see. It could be journalists, it could be enthusiasts. This is Globe Life Field in Arlington, Texas, and if you're a baseball fan, then you know the Texas Rangers are the ones that won the World Series this year. But you can see in the bottom right of this image, that's where the stadium was constructed over a number of years, relatively close to their existing stadium in the top right. But monitoring these things, could be interesting to insurance companies, to cities and so forth, but a great example here of construction in this sense. And then, lastly, there's also the enthusiasts that are monitoring a lot of global conflicts right now. And in this case, the Russian defense minister mentioned that there was an attack that came from Ukraine into Russia, but there was no damage. And we had an enthusiast who on Twitter took a before and after picture of a particular location that was targeted and could prove the defense minister maybe wasn't telling the truth, that an airplane, a large plane was destroyed in this attack, and posted that and got a lot of attention on Twitter, that's for sure.
Very interesting. So we've covered a variety of use cases for Earth observation data, and you covered some value add propositions that Skywatch offers. So obviously this process isn't easy managing Earth observation data. So I want to ask the audience first, before we get into it, what are some of the challenges that you all think may be faced by those who have to use Earth observation data? If we could take a quick look at those responses. Awesome. So all of the challenges that we've posed are challenges that Skywatch helps solve. So if we could go back to the deck. So how has Skywatch evolved to solve some of these problems that we see are faced by Earth observation data users?
Yeah, sure. So, thinking about how Earth observation was delivered, we'll go through a little brief history of how that's happened over the years. So, starting in the 1970s, if you wanted data delivered, it was delivered by truck, and you got punch cards. And in this particular example, this room is filled with punch cards. That's about 4 gigabytes of data. And for context, that's roughly the size of one Earth observation image today. Now, of course, imagery was different back then, but punch cards were the method of delivery. You moved to the 80s, and it got a little bit better. 9-track tapes were the way that data was distributed to a large degree. So the USGS would make these available for $400. You could buy Earth observation. It was open data, but that was the cost associated with the tapes and the shipping. And interestingly, it was the Russians actually who were the ones who bought the most data from the USGS. Moving into the 90s, you started to have some desktop GIS emerge. It was relatively in its infancy. There wasn't a lot of computing power behind it, but that started to change things as well. And then you get into the 2000s, and now we've got about 50 Earth observation satellites in orbit. And data storage costs started to drop significantly. So the graph on the right is maybe difficult to see, but in dollars per gigabyte of storage over time between 2000 and 2020. On the left, you can see in the y-axis the cost, and on the bottom you've got time. And you can see that kind of like 2007, 2008, 2009, all of that cost started to really fall out, and so that made a big difference as well. But it was still challenging in this time. There was logistical challenges to move this data around. So if you move into the 2010s, now this is the dawn of cloud computing, and AWS launched in 2006, but it was really in the 2010s when Kubernetes and Docker came into existence. And we also saw the acceleration of commercial Earth observation funding from venture capitalists. So the graph on the bottom right is showing that investment in space companies over time, and you see a big spike between 2014 and 2015. 2015 is when there was about almost $2 billion invested from private ventures. So the second half of the 2010s, it was really the rise of lower cost, good enough revisit rates from these particular satellite operators, but the data distribution systems were still pretty immature. So see in the bottom right, FTP is sort of the way that data has been delivered for a long time in the industry, and it still continues today, surprisingly enough. So if we go to the last 5 years, really, we've replaced a lot of those slower systems with cloud-based infrastructure. And this is actually a post from the AWS blog. I know, Quentin, you're familiar with it. I don't know if you want to maybe describe some of the details here.
Yeah, sure. I really like this example because this is not only showing how AWS can be used for space applications, but how AWS can be used in general. And so if you need to procure Earth observation data in an event-driven manner, you can process that data from L0 to L1 or L1 to L2 based on event-driven data delivery. And that really reduces your burden to receive data. And so this is how AWS has begun reducing the barrier to entry. But if you would talk more about Earth observation and how you see it changing.
Yeah, for sure. So, what we see in the future is really algorithms replacing eyeballs. Historically, an image comes down from space, a human interprets it and writes a report, delivers that information to someone. But we see that as a much more closed loop autonomous system where, a satellite takes an image, there's algorithms that respond to that image and classify things that could go into a thing like an autonomous tractor. It fertilizes the areas that need to be fertilized. We monitor the growth, and then that loop starts again, that observation loop starts again.
So we've taken quite the journey from the 70s till now. But if you could take us through your thought process, it's 2017, you're a young startup. Take us through why you decided to build on AWS.
Yeah, so one of the great things about working at a startup is you generally don't have legacy code. So we had a vision in 2017 when we really started building out our platform. We had a few things we wanted to do. So the first was we wanted to embrace a microservices architecture, allow us to deploy multiple times a day in a really simple way, to scale, to have different developers working on different things really easily. The second was we wanted infrastructure as code, so things like CloudFormation or Terraform, the ability for us to define all those things in our code. And then the third was, I think, maybe a little relatively ambitious in 2017. We had the goal of 100% serverless. So back in 2017, Lambda was around and step functions were around, and so was DynamoDB and a few other things. But they had a lot, they're not the same products that they are today. They were smaller in terms of capacity and memory limits and those kinds of things. But our goal was that ideally, when something was running, we were paying for the compute for it. And when nothing was running, we weren't paying anything. So that was driving our thought process of being 100% serverless. So we also wanted to lean into the proprietary features of AWS. So some people talk about cloud lock-in, and maybe that's something they would try and avoid, and they build Docker and Kubernetes and those kinds of things. We really leaned in because you get a lot of value from embracing that. And you can debate with other people about cloud lock-in, but we were really excited to use some of these advanced features. And if you go to the next slide, it's a bit of an eye chart, but these are some of the AWS services that we use. So across the top are kind of our big ones in terms of step functions in Lambda. When images get too large to process in Lambda, we use Fargate. We take a big data approach, actually. We break the images into smaller pieces. We run them in parallel, and then we bring them back together at the end. Things like API Gateway and S3 obviously have been a big part of our platform as well.
So there are obviously a number of serverless services here on the screen, but to call it a few, specifically the compute services, Lambda and Fargate, how has using these serverless platforms helped you as a business and ultimately your end customers?
Yeah, so really for us, it came down to these predictable marginal costs. So if you're running a number of EC2 instances, or even spinning things up and pulling them down, it's really difficult to know exactly how much that image costs to process through the platform. But with serverless, you can do all of that. You can basically bake that into your cost of goods sold, and you can measure, if you trace through the processing of an image, through all the different lambdas and microservices and state transitions and step functions, the size of those things, the duration, you can add all of that up and you can get an actual cost per square kilometer of imagery that you process. So,
audience, you've been sharp thus far, so we're going to throw a curveball at you. Now that we've understood that these serverless services help with enabling predictable marginal costs, how much do you all think a square kilometer of Earth observation data with serverless technology or processed with serverless technology would cost?
And for the experts in the room, this would be a 70 centimeter product, so high resolution imagery.
Alrighty, and if we could take a look at the results. So we have a variety of answers here.
Interesting.
A variety of answers. I think we'll be surprised. So if we could go back to the slide deck. So if you could tell us a little bit about the path an image takes from request to delivery of the image, so we understand the cost a little bit better.
Yeah, I'd love to, and hopefully shed some light on those answers at the end. So of course, if you want to take an image, the first thing you need, you want to take an image of a conference you happen to be attending. The first thing you need to do is communicate that information to a satellite operator that's capable of finding a satellite to help you capture that image. So all of that communication happens between the ground and the space, and between the ground network, which is actually finite points distributed all over the Earth. So there are these discrete windows in between which you can communicate with the satellite. But let's say you do that, you maneuver your satellite to the target area that you want to capture your image over. It opens its aperture, collects that data. You then have to process that data just a little bit. Quentin had mentioned L0 data. This is kind of raw data. There's quite a bit of processing that goes on between converting the photons that the CCD captures into rendering that as an image the way you and I might expect to see it. So once that raw image actually lands with us, next slide, please. There's still some additional processing. The Earth is a curved surface, so you have to reproject that into a flat image domain. We mentioned earlier that you might capture the image across several different wavelength bands. So you need to compose those together, which helps to sharpen and enhance the image. And then for us and our customers who might want to know where there is visible ground on the image, we might also do some machine learning and do cloud detection to be able to provide accurate cloud masks for where visible surface is. But of course, the ultimate application that our users are seeking to use this imagery for may have a variety of different output types that they need. True color, the way we see the world, is not always the best way to be able to tackle your use case. Someone who's studying ice flows or floodplain development might want to look in false color infrared. And so to actually derive the final output type that a customer wants, we need to do additional processing. So all of these components need to be customized and tailored to whatever that use case is. So this is a bit of a high-level overview of the architecture that we use here. And as Joel said in that big slide of logos, it's primarily step functions and lambdas running there. But we do everything from systems in blue, which capture how our users might want to access that data. In gray, there's a lot of data distribution to be able to find the right source, bring in the right data, convert it to a format that our users can use. And then in teal is a lot of the image processing, so that orthorectification, pan sharpening, but also the machine learning components to be able to do the processing that's necessary. And if we take a little bit closer look at some of, let's say, the image processing, for example, you can see on this slide, all of those components, whether it's, converting it to a cog or tiling, as Joel had said, to break up the image into smaller components. We want each of those to be serverless. So we use lambdas there, Fargate if the image is particularly large or we need to do complex geometry for the processing. But having it all be serverless allows us to spin up exactly the components that we need and do the processing for the specific amount of time we want. If the image is particularly large, sometimes we see 100 gigabyte image for a single image from really high resolution aerial balloons, for example. Then we want to be able to tile those into separate components. And for each of those tiles, we can spin up identical but individual operators that will do exactly the same type of processing before we stitch all of that imagery together. And in the machine learning domain, being serverless has really been helpful because we may have a live model that's running and doing our processing, whether it's cloud detection or some other type of machine learning algorithm. And as we iterate on those algorithms and want to deploy new ones for our customers, we often run those in parallel in what we call shadow models beside there. And so we can do inference en masse across a host of different images, but also across multiple models in parallel. Collect all of that data together in something like S3, and then do our evaluation before deploying those models into production itself. So really, the key here is that serverless being able to just turn on and off every single piece of what we need to do for the processing as the situation demands it. And of course, if we had to deploy and manage all of that infrastructure ourselves, it would be quite a hassle. And so, things like code build, code pipeline, ECS for the container service allows us to really abstract away all of the operational costs and reliability that we need. That's all taken care of by AWS. And that also facilitates rollbacks if we need in case of an emergency. So, a serverless architecture that's event-driven allows for automatic scaling and short-lived functions, allows us to deliver that imagery for the votes for 12 cents per square kilometer.
So serverless compute has obviously been really critical for you all's development and adding value to the market. But are there other places that you see being able to add value to the delivery of Earth observation data?
Yeah, absolutely. So, as we move forward, we're in the business of democratizing data. We want as many people to have access to it as possible. And so one of the ways in which we can do that the most effectively is by driving down those operational costs. So one of the things we're now starting to really consider is how we push some of that critical processing higher up the funnel. Imagine you do your communication with the satellite, you do your downlinking, all of that processing that's necessary, and it turns out your image is fully cloudy, right? Well, you don't want that. So what if you could take all of that processing, all of that evaluation, initial evaluation, and push it up onto the satellite itself, right? So what we're trying to do now is really leverage edge computing in space. And by pushing that processing to the top of the funnel, we can ensure that the data that's actually downlinked from the satellite is really only the usable data that a customer might want to access. And to that effect, Skywatch is part of the Edge Computing in Space Alliance. So this is an alliance of organizations who are really dedicated to advancing standards of practice to ensure and accelerate the adoption of edge computing in space. To go along with that, we've developed a system called TerraStream Edge, which really gives satellite providers, access to a host of our state-of-the-art machine learning models so that imagery can be evaluated and even scene level data extracted from that. And in the future, we really see perhaps customers not even needing imagery, the entire image downlinked, but just the data, the extracted data insights as well.
So just to understand how relevant bringing some of this processing to the edge would be for Earth observation data audience, how much of the Earth do you all think is covered in clouds every day? This data would be relevant because, as Alex mentioned, downlinking a cloudy image not only costs the satellite operator money, but it costs the company who requests this image money. So we want to make sure that process is efficient as possible, and so understanding how many clouds cover the Earth in a day helps us understand the efficiency this drives. So if we could take a quick look at the results. Oh, again, we've got a split audience. Made them tough. So before we get into the actual numbers of how much of the Earth is covered in clouds, if we could go back to the slide deck. Could you tell us a little bit about the specifics of how Skywatch's cloud detection algorithm would work?
Yeah, I'll save the really fancy stuff for Alex, but in general, what we try and do in space is basically make a Boolean decision. Should this image be accepted or rejected? And in this case, obviously the image on the left is clearly cloudy. The one on the right is not. But when you have 70% of the Earth covered in clouds every day, you have the opportunity to have pretty massive savings. And it's challenging because there's a lot of things that look like clouds. Snow looks a lot like clouds, so you need to be able to disambiguate things like that. Beaches, sometimes they're really bright next to a dark ocean. Those can look potentially like clouds as well. So that's a use case that we're excited about with edge computing, to be able to save the downlink and processing for 70% of the Earth being covered in clouds every day. Another use case that we really like is what we call onboard clipping. So when a satellite takes an image, sometimes the smallest size it can take is hundreds of square kilometers. So by the time you open the satellite's aperture and you close it, it takes varying degrees of time, but it captures a lot of imagery. Now a customer may only want, say, 25 square kilometers of imagery in that area. So if we can clip a 500 square kilometer image down to 25 square kilometers and save that 475 square kilometers of downlink and processing, that's another value add and cost savings that can be passed on to the end users. And then lastly, sort of the fancy use case that lots of people like to talk about is the object detection in space. So it could be something like detecting the early signs of a forest fire and be able to send just the information down and say, hey, we really need to get fire officials out to this particular location. Or it could be other objects. There's lots of great use cases in the media about counting cars in parking lots to predict the revenues of JCPenney's, for example, or port monitoring or airport monitoring as well. So lots of great object detection use cases where that information could come down from space as well.
So now that we've seen how serverless can add value and we've added value with the edge compute, how do these technologies come together to create a whole solution?
Yeah, it's a really great question. So, to accomplish this, we're really trying to take a lot of the lessons that we've learned with building a ground-based system on AWS to be able to deploy an equivalent type of infrastructure in space. And one of the lessons that we've learned is really having a really distinct separation between what needs to be the ground segmentation and the space-based segmentation. Satellite hardware is very sensitive to perturbations from the surrounding environment. There's ambient radiation, and these objects are often moving at tens of thousands of kilometers per second around the Earth in orbit. So you really want to only turn on those systems to do processing in exactly the way you would have in a serverless architecture with an AWS infrastructure. So that's really critical to how we're now developing this for, to be able to reduce costs at the edge.
So if serverless helps you reduce the cost, and then having some of the processing done at the edge helps you further reduce the cost for both the operator and the consumer, where's Skywatch going next?
Yeah, we're excited. We can share a couple of the things on our roadmap. So the first thing really is we look at these areas of friction for our customers. And the first one, maybe not so related to edge or to ML, but is really semantic search. So if you can imagine a large organization captures lots of satellite imagery, it may be on cloud storage, it could be on hard drives, but knowing what the organization owns and how to find it is challenging. So we did an experiment, it actually turned out really, really well, where we took an image, we passed it through Amazon recognition, and we got returned back all of the predictions of what was actually in that image. We didn't do any customization to the model. But by doing that, in this particular image, we got back things like port and ship and city and water, and so surprisingly quite good out of the box. Now that image, we put those as tags in our platform, and now they're searchable. So you can imagine if you took all of your imagery that you purchased, if you have thousands of images, you run them through recognition, you get back these tags. Now we've essentially made it searchable. And certainly a lot more we can do here, but just a very quick experiment was something we were excited about and we'll be developing over the next few months.
Yeah, and on the machine learning front, SageMaker is essential for a host of different models that we talk about. I think object detection, cloud detection, these are sort of the intuitive use cases, but our customers also have to deal with image defects of that come in a variety of different forms. The aperture may malfunction during the image capture, so an image could be misaligned, it could be blurry, there could be noise and other artifacts, right? So SageMaker is the workhorse of a slew of machine learning models that we use to be able to derive really good data and maximize fulfillment for those customers.
Yeah, the really important part of that is when you're in a machine-to-machine world, if we're delivering data and no human is in the loop to QA it, you need something like this in place so that it'll intercept poor quality imagery so it doesn't go to an end customer. And the last item that we'll share is a natural language interface, and certainly the Gen AI stuff has certainly been talked about a lot so far this week. And using things like Amazon Bedrock to transform a natural language request into a complex API call is something that we've experimented with as well. So being able to say, hey, I want an image of New York City, Central Park in New York City next week, translating that into a number of different attributes is something that we're excited about too. So that brings us to the end. And so thank you all for staying. But in summary, some of the takeaways that we want you to think about are, Earth observation data right now, it's much more affordable than it was, but there's still a long way to go. And serverless has been really key to lowering costs and will be key to continuing to do that. We also really believe that edge computing is extremely important. It's going to decrease costs significantly, and also reducing latency is a requirement for a lot of different use cases as well. How quickly can we get that capture to insight on the ground? And then finally, at the end of the day, what we believe is people ultimately won't be looking at pixels forever. They really just want those insights. So how do you transform that in a scalable, efficient way, maybe on the edge, maybe on the ground, but in a way that can have that low latency delivery of information that people can trust? Those are the things that we're excited about. So thank everybody for coming. Thank you all, and appreciate it.
Thank you.